Hello and welcome to Lesson 2T. I can use theorems about parallel lines to prove properties of triangles. So this is kind of an interesting lesson because we're going to take several different theorems about parallel lines and apply them to the use of triangles. And the first and most important thing that we're going to learn about is the parallel postulate. And what the parallel postulate says is that if I have any point out in space and a line, I can draw exactly one line through that point that is parallel to the given line. And while this postulate may seem pretty obvious, and in fact you used it a lot in Algebra 1 when you were writing equations of parallel lines, just you didn't even know it, we are going to use it to help us prove that triangles have exactly 180 degrees. Looking down here, I want to prove that the sum of the angles in a triangle is 180 degrees. Well, I'm going to do that by drawing a line that is parallel through point B, that is parallel to AC. So I have created this line where DE is parallel to AC. And what's really nice about that is I end up creating all of these alternate exterior angles. So if you look at this, angle A and angle 1 are alternate interior angles, which means that angle 1 must be congruent to angle A. And then if you look over here, angle C must be congruent to angle 3 by alternate exterior angles. Angle 3 must be congruent to angle C. And then, of course, our original angle B, which we can no longer call angle B, but angle 2, he's right there. He's my third angle of the triangle. Well, if you look, these three angles, 1, 2, and 3, they're all coming together to create a line. And when angles come together to create a line, then we know that the sum of their measures must be 180. Then we know that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 must be 180. Well, therefore, we know that the measure of angle A, which is angle 1, plus the measure of angle 2, or we could call this measure of angle B, but remember we can't really call it B anymore, plus the measure of angle C must be 180. Well, we just proved that the angles in a triangle all add up to 180 degrees. Granted, we did it very informally, we didn't use a T-chart, but that's okay. We were able to use that parallel postulate to help us prove that the angles in a triangle add up to 180 degrees. Now, there's some other pretty cool things we can use this postulate for. When we're over here, I want to talk about types of angles in any polygon. When we're looking at a polygon, we've got two types of angles. We've got interior angles and exterior angles. And interior angles are exactly what you think they are. They're the angles inside the polygon. So looking at this really irregular pentagon I've made here, this guy right here is an interior angle, right? Well, an exterior angle is an angle that forms a linear pair with an interior angle. So if I take a side of a polygon and extend it, the angle that forms right here, this guy here, is an exterior angle. Note, if I just draw any random line, that's not going to create an exterior angle, right? It has to be an extension of a side. So right here, this is an interior angle, and then this guy here where I wrote exterior angle in typeface, that's the exterior angle to this interior angle. Now, when we do this in a triangle, some really special things happen. Specifically, when we create an exterior angle like angle 4, it turns out that angle 4 is going to end up being equal to the sum of its remote interior angles. Now, what does it mean to be a remote interior angle? Well, if angle 4 is an exterior angle, then the remote interior angles are the angles of a triangle that do not form the linear pair with 4. So if 3 is the interior angle that forms the linear pair with 4, then 1 and 2 are the remote exterior angles. So these guys are the remote exterior angles to angle 4. All right. Angle 3 and 4 form a linear pair, right? So there's a really cool theorem out there that says that when we have a triangle, the measure of an exterior angle, so my exterior angle, is going to be equal to the sum of the remote interior angles. So basically, that angle 4 would be equal to the sum of angles 1 and 2. I want to prove to you why that is. It's actually a pretty sweet proof, guys. So in this proof, we're given a triangle with exterior angle 4 and remote interior angles 1 and 2. And I want to prove that angle 4, that the measure of angle 4 is equal to the measure of angle 1 plus the measure of angle 2. Well, let's go ahead and fill in our t-chart. And guys, when you fill this in, feel free to use shorthand. I don't want to reproduce that whole sentence, that's annoying. So again, mathematicians are lazy. Triangle with exterior angle 4 and remote interior angles 1 and 2. So what can we say? The first thing I can do is I can look at the fact that we're given a triangle. Well, what do we know about triangles? We know that the angles in a triangle add up to 180 degrees. So I'm going to write that down next. And we know that the angles in a triangle add up to 180 degrees by the triangle angle sum theorem. What else do we have in this picture? We also have a beautiful linear pair, 3 and 4, quite lovely. And we know that linear pairs are supplementary and that supplementary angles add to 180. So I'm going to go there next. Now, I really hope you guys are recognizing that a lot of these steps come in the same sets, so to speak. So anytime I'm talking about two things being a linear pair, I'm then going to say that they're supplementary, and then I'm going to say that they add to 180. That is always a sequence that's going to go together. Well, that's what we've got here. 3 and 4 linear pair, 3 and 4 supplementary, therefore 3 plus 4 equals 180 by the definition of supplementary. Now, something really awesome has happened. I've got two large phrases, here and here, and they're adding to the same number, 180 degrees, right? Well, when I've got two phrases that are adding to the same number, I can set them equal to each other by the transitive property. And so that's what I'm going to do. So we set them equal to each other. Well, I really like that because while I'm looking at these, I can see that I've got the measure of angle 3 here on both sides. Well, that's great because if it's on both sides, it can cancel with subtraction. So that's what I'm going to do in step 7. Step 7 allows me to say that the measure of angle 1 plus the measure of angle 2 must be equal to the measure of angle 4 by subtraction. And remember, we never shorten the word subtraction because it could be confused for substitution. Subtraction, property of equality. That isn't exactly what I'm looking for, though. I'm looking for the statement measure of angle 4 equals measure of angle 1 plus measure of angle 2. I'm so close. Last thing I need to do is take this and flip it around. So my very last step, step 8, I'm going to say that the measure of angle 4 is equal to the measure of angle 1 plus the measure of angle 2 by the symmetric property of equality. And we have finished the proof. Yay. All right, so we've done all this work now proving this theorem. Let's now actually use it in practice. So when we're looking at diagrams like this, there are a couple of things I can see immediately. I know that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3, that's always going to equal 180 because the angles in a triangle add to 180. I know that the measure of angle 3 plus the measure of angle 4 is going to add to 180. I also know that the measure of angle 1 plus the measure of angle 2 is going to add to the measure of angle 4, right? That's the remote interior angle theorem, the thing we just learned and just proved. So we're going to use these 3 pieces of information to help us solve questions 1 through 4. So question 1, I have that the measure of angle 1 is 80, the measure of angle 2 is 26, and I'm looking for the measure of angle 4 and the measure of angle 3. Well, I can get 4 immediately because I know that the measure of angle 1 plus the measure of angle 2 equals the measure of angle 4. So I'm going to start there. That's 80 plus 26 must equal the measure of angle 4. That means the measure of angle 4 must be 106. I like that one. That one was nice. Well, I also know that 3 plus 4 must add to 180, so I can say that 106 plus the measure of angle 3 must add to 180, so the measure of angle 3 must be 74. All right, guys, I want y'all now to go through and answer question 2 on your own. Well, I know that 1 plus 2 equals 4, so I plugged in 54 for angle 1, 102 for angle 4, and I got the angle 2 is 48. I also know that angle 3 and angle 4 are linear pairs, so 3 plus 4 must equal 180. So a measure of angle 3 plus 102 equals 180, so angle 3 must equal 78. All right, guys, I now want you guys to go and do question 3 on your own. All right, guys, here's how I worked the problem. There are many, many ways to work this problem. This is just one example. And finally, let's look at number 4 together because we've got some variables. Doesn't change how the problem is written, right? So I don't know the measure of angle 1. I know the measure of angle 2 is 30, measure of angle 4 is 10x, and the measure of angle 3 is 8x. Well, I'm going to start right here with 4 and 3 because I know that measure of angle 4 plus the measure of angle 3 is going to be 180 because they're a linear pair. So I can say that 10x plus 8x must equal 180 because they're a linear pair. That's 18x equals 180, so x must be 10. All right, that means that the actual measure of angle 4 is 10 times 10, which is 100. And the actual measure of angle 3 is 8 times 10, which gets me 80. All right, now I know that measure of angle 1 and the measure of angle 2 added together must equal the measure of angle 4. So that means the measure of angle 1, which I don't know, plus the measure of angle 2, which is 30, that must equal the measure of angle 4, which is 100. So that means I get that the measure of angle 1 ends up being 70. And that answers all of my angles. All right, guys, thank you very much. Look at the MML homework, and we'll see you in class.